performance. Last week, all we did was kind of go over the syllabus and a quick intro. Today, we'll start actually diving into the material, and so I'll have slides that I'm going to talk you through. Got a couple pictures or videos that I'm doing to show you some things. I'll record those. Have recorded those down in the vehicle training center, and I have some videos. Some of them are a little bit hokey, but some videos that I found on YouTube, basically, that I'm going to show you. So between my talking you through slides, showing you videos that I've done at the training center, and videos that I found on YouTube, we'll see if we can't get through some of this material. So we're going to start out, just go on to Blackboard so you can see where the material that I'm working off of is. So let me get signed into Blackboard here. And we'll just choose any one of the lectures. You know, these are all the same. So top of the screen is the Monday morning section. If you're in Monday afternoon or Monday night, it's the same thing. Whichever AU-264 you have showing is the one, of course, that you're going to go to. So under lessons, we have Module 1 here. And under Module 1, there's a link to click on Slides. Let's get that going. Okay, so here's our first set of slides, full screen here, hopefully. Talking about basic engine operation, which is going to start by reviewing some terms like TDC, BDC, what does stroke mean? And this should be stuff that's reviewed to you if you took engines. We'll talk about vacuum and pressure, and then review the four-stroke cycle. And we'll probably somewhere in the middle of that, probably after the compression stroke, maybe is about as far as we'll get today, and then we'll continue next week with the power stroke and the exhaust stroke, and then talk about engine air fuel requirements. They do vary with different engine operation, operating conditions. Obviously, when you stomp on the accelerator, you're going to need a richer air fuel mixture. When you're coasting, it's going to be leaner. Cold engines require more fuel than warm engines. So we'll talk about all the things that change as you drive down the road. And then we'll talk about the effects of compression, the effects of not having enough compression, the effects of having too much compression, and finish up this set of slides with an overview of spark timing. And I actually have another set of slides that I can use for that, for the spark timing, just to talk about that a little bit more. So let's start with this first one here. Top dead center. What does that mean? So the word top, we're talking about where is the piston in the cylinder. So piston's at its highest position in the cylinder, and the crank is at 0 degrees. In other words, that connecting rod is right down the middle of the cylinder. The crank is not off to the side at all. At bottom dead center, the piston's at its lowest position at the bottom of the cylinder, and the crankshaft journal is straight down, the furthest away from the top of the cylinder at 180 degrees of rotation. And again, that connecting rod should be right down the middle of the cylinder. So all a stroke is, we talk about the intake stroke or the exhaust stroke. All it is when the piston either moves from top dead center to bottom dead center, or when it moves from bottom dead center to top dead center. It's 1/2 of a crankshaft revolution. So think about that. You got a 4-stroke cycle. So intake stroke, piston moves from the top to the bottom, the crank moves from 0 to 180, half a rotation. Compression stroke, piston moves back up, crank moves from 180 to 360. So it's now gone around a complete turn, 360 degrees. Half a turn was the intake stroke, the other half was the compression stroke. Then you have the power stroke. So again, piston moves down, crank goes a half a turn. And the exhaust stroke, piston moves up, crank goes the final half turn. So to get through one 4-stroke cycle, it is 2 complete rotations of the crankshaft. The next point, piston speed is not constant. So as you get near the top, the piston's approaching the top, it's going to change direction, right? So imagine you're driving your car and you're going to go backwards, right? You're maneuvering in a parking lot. So you're pulling forward before you can put it in reverse and go backward. At some point, you have to slow down to a complete stop and then start accelerating in the opposite direction. And then you come to a complete stop and start accelerating in the opposite direction again. So if you think about the piston and the cylinder, it reaches maximum speed, halfway down the cylinder, and that crank is at 90 degrees or 270. It's at right angles to the center line of the cylinder. So one of the reasons this is important, I just want to talk, when we talk about the intake stroke, we'll talk about it a little bit more, but the piston moves down on the intake stroke. When it gets to the bottom, it's at a dead stop. And when it's close to the bottom, it's very close to being at a dead stop. It's moving really, really slowly at that point. And after it goes past the bottom, it's still moving really, really slowly until it accelerates up and reaches maximum speed again halfway up in the cylinder. So there's a big period of time at the bottom of that stroke where the piston is either moving very slowly or not moving at all for a split second there. And during that time, if you leave the intake valve open, air can continue to rush in even after you go past bottom dead center and the piston is starting to move up again. It's moving so slow that if air is coming in at a high rate of speed, it can still come into the cylinder well past bottom dead center. And that maximizes how much air we can get into the cylinder on the intake stroke. Every engine is designed a little different. The valve timing, depending on at what RPM they're trying to make their power. So let's talk about what it is that actually gets air into the engine. So we have naturally aspirated engines, as you know. This means that the only thing pushing air into the cylinder is atmospheric pressure. And then, of course, we have forced induction turbochargers and superchargers that take some sort of a compressor or an air pump and push the air into the cylinders. But still, for most, I think, we're talking, naturally aspirated, which means atmospheric pressure. So what causes atmospheric pressure is actually the weight of the air above you. So if you're standing at sea level, the entire atmosphere is above you and pushing down on you. At sea level, it's about 15 psi. As we start going up higher than sea level, so if we go up in the mountains, or if you're up in an airplane, for example, now some of the atmosphere is below you and some of it is above you. So you don't have the weight of the entire atmosphere on you anymore. You've got the weight of part of the atmosphere. So the atmospheric pressure is actually less the higher you go. I know in a small plane, which I fly a small plane, the higher you climb, the less power your engine is going to make, because you're just not getting as much air into the cylinders, not filling the cylinders as well. Also, the higher you climb, the less fuel you need to mix with that air. So we actually start leaning the air-fuel mixture out when we get up to altitude. If we get up into the 14,500 feet level, that's when, in a small plane, you actually need supplemental oxygen. So atmospheric pressure is caused by the weight of the atmosphere, and it is dependent on a lot of things. One of them is your altitude. So vehicles up in Denver are operating under different conditions than vehicles in Buffalo. The other thing that can change atmospheric pressure is the barometer reading. So on a stormy day, atmospheric pressure is pretty low. It's really low in the eye of a hurricane or inside a hurricane. On a nice sunny day, the atmospheric pressure is probably much higher. So standard is, like 29.92 inches of mercury, but sometimes it's a nice high pressure system. It's up over 30, or low. It's down below that. It's variable. So the car has to be able to, as it's driving, it has to be able to deal with changes in atmospheric pressure. And so it has to have some way of measuring that, or measuring how much air is actually making it into the engine. So one term everyone's familiar with is vacuum. And so vacuum is anything less than atmospheric pressure. So if I had a, let's say a Pepsi bottle or something like that, and I took it up in an airplane and put the cap on up there where the pressure is low. So up there, it's the atmospheric pressure at the time, and I seal that bottle, and now I land the airplane down on ground level where it's higher pressure. Now we have a pressure differential. We have higher pressure outside the bottle than we do inside the bottle. If I open that bottle cap, assuming the bottle hasn't crushed from the excess pressure, but if I open the bottle cap, air is going to flow into that Pepsi bottle. So in other words, the Pepsi bottle is going to act like a vacuum, and it's going to seem to like suck air in. And what that really is just a pressure differential. So in an engine, when we open the throttle plate, assuming that the pressure inside the throttle body or inside the intake manifold is lower than atmospheric, air is going to flow in. And the bigger the difference, the faster the air is going to flow in. So when we measure vacuum, we're talking about anything less than atmospheric pressure. And when we look at a gauge, and I'll do that in a minute, we'll see that vacuum is measured in inches of mercury. So what's a lot? Well, an engine that's running at idle, typically vacuum in the intake manifold is somewhere around 20 inches of mercury. They say like 17 to 24 or something like that. Somewhere around 20 inches of mercury. And vacuum is caused when air is removed from an area, lowering the pressure. So air at higher pressure rushes in to fill that vacuum. If there's a restriction in the intake airstream, that'll cause the vacuum to increase because air can't flow in as much. So when we close the throttle on an engine and block off the incoming airflow, we are going to see higher vacuum numbers, meaning lower pressure, right, in the intake manifold. When we open the throttle and let air rush in, we're going to see more pressure or less vacuum. So we got to kind of think of vacuum and pressure as really just two different sides of the same thing. So let me cut away now and go to a little picture of a vacuum gauge. Here we have a typical vacuum pressure gauge. So over here on this side, clockwise, is pressure, and this outer ring here is PSI, and it goes from 0 up to 15 PSI. So this was used for checking fuel pressure on old carbureted cars where the pressure coming out of that mechanical pump was only a few pounds, maybe 5. And on this side over here is vacuum in inches of mercury, and it goes from 0 to 30 inches of mercury. Typical automotive intake manifold vacuum readings are going to be somewhere in the 20 range. 17 to 22 is considered normal, I think. So the thing that's most interesting, or that I want to point out, right? This is the port that you use to connect it to a vacuum source. So a hose from here maybe to the intake manifold, and right now you notice that it's open and not connected to anything. So what it's sensing is atmospheric pressure. A little while ago I told you atmospheric pressure is about 15 psi, yet
the gauge here is reading 0. How do we explain that? Well, the way we explain that is by saying that 0 on this gauge doesn't mean there is no pressure. What it means is 0 equals atmospheric pressure. And so if this gauge needle moves to the right or clockwise, it's showing us that we have a pressure that's higher than atmospheric pressure. If it moves to the left, it's showing us that we have a pressure that's lower than atmospheric pressure. Now, the only place you have 0 pressure, no pressure at all, would be outer space. So even if this needle is to the left somewhat, all that means is the pressure is somewhat less than atmospheric. It doesn't mean there's no pressure at all. So to put this into an automotive idea, if I have an intake manifold that has 20 inches of mercury, so we would call that vacuum, right? That's much less than atmospheric pressure. And now the intake valve to cylinder number 1 opens, right? The pressure in cylinder number 1 is even less than the pressure in the intake manifold. So we're calling it a vacuum, but it's still higher or more pressure than the even more complete vacuum that's in the cylinder. So what happens? Air rushes from the intake manifold with less than atmospheric pressure into the cylinder with even less pressure than that. So sometimes, you've heard of a MAP sensor, that's manifold absolute pressure. That's really what they mean. It's, it's more than a perfect vacuum or outer space, but it's less than atmospheric if the gauge is over this way. If you take a turbocharged car and you're driving down the road, there are times when you're going to see this gauge needle clockwise of 0. And there's a term for that. It begins with a B. I know you know what it is, right? So when the turbo is spinning and providing pressure into that intake manifold, the gauge needle is going to be somewhere up around here. So you could plug this into your intake manifold, use it as a boost gauge. Sitting at idle with the turbo not really spinning. Oh man, now I gave up the word, right? Boost. With the turbo not really spinning, you're going to see something less than atmospheric. We're going to call that a vacuum. You start driving and jump on it, it's going to boost up, 8, 10, 12, 15. It depends on how big of a turbo and how strong your engine is. So into, what we would consider positive pressure. So bottom line, the 0 on the gauge means atmospheric pressure. Anything that we call a vacuum just simply means less than atmospheric pressure. And anytime the gauge reads this way, it's more than atmospheric pressure. So for a car, here's the pressure outside of the throttle plate, out under the hood, in front of the car, around the car, right? Here's the pressure in the intake manifold, maybe at idle, and then the pressure in the cylinder is going to be somewhere less than that, right? So air is going to flow from the area with atmospheric pressure towards the area of lower pressure, which is the intake manifold, and then from the intake manifold towards the area of even lower pressure, which is the cylinder. When I open the throttle, so I'm sitting here at idle and my gauge needle is maybe at 18 or 19 inches of mercury. When I open the throttle, what I'm doing is I'm letting a whole bunch of atmosphere into that intake manifold. So this gauge needle is going to go up closer to atmospheric when I stomp on the accelerator, because I'm letting air in and jacking the pressure up. Then when I take my foot off the gas, it's going to go back down. So one thing we can do with vacuum testing, we can plug that gauge onto a port on the intake manifold, see what we're getting at idle, make sure it's enough. If it's way up here, we might have a vacuum leak or we might have valve problems or something, right? So make sure it's enough there. And when you hit the gas, you should see this needle get very close or all the way up to atmospheric pressure, meaning that we've taken the throttle plate out of the way and let the atmosphere flow into that intake manifold. Then if the engine's moving fast, so it needs a lot of air, and we close the throttle, you might see this needle drop way down here because we're blocking off any incoming airflow, yet the engine is still looking for it, if you will. So that's about it on the vacuum gauge.
So before we go back to the slides and move on, I have a video. It's a little goofy, you know. It's something I found on the internet. I want to share that with you, and it talks about atmospheric pressure, and then we'll continue on with the slides. So let me just find that video here. We'll share this with you. It's called atmospheric pressure, and I am gonna turn off my camera here. Sorry about the commercials.
If you manage a team, you have to try Monday.com. Monday.com is a platform to track everything you're
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist, because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
Okay, so as promised, it was a little goofy, but
Good grammar and
Yeah.
spelling are important.
pardon me.
But if you want to write essays that inspire,
I guess I'd better kill that. There we go. Okay, sorry about that. The next video started playing, so I had to take care of that. Growing pains, first lecture of the semester, so I don't have things quite down yet. Anyhow, so now we'll continue on the slides and start talking about the four-stroke cycle a little bit more. Okay, so let's go back to the slides here. Shut me off, go back to this. And where were we? All right, we were talking about atmospheric pressure, vacuum, stuff like that. So hopefully you've got a pretty good handle on vacuum pressure, atmospheric pressure, and what makes a naturally aspirated engine run. So I mentioned this when we were talking about the vacuum gauge, that outside the throttle plate, you have atmospheric pressure. Between the throttle plate and the intake valve, there's intake manifold pressure, which you saw was something less than atmospheric. Depending on where the throttle plate is and engine RPM and stuff like that. And then inside the cylinder is where the pressure is the lowest, and that's where the air is eventually going to flow into. So one thing that's really important to understand, throttle opening and engine speed are two things that really affect how much air flow into an engine. So it's kind of obvious that when you stomp on the accelerator pedal, and you're really not hitting the gas, you're really hitting the air. You're opening a throttle valve, a throttle plate, and letting air rush into the engine. So when you do that, needless to say, airflow goes up, and the amount of air flowing into the cylinders goes up. On the other hand, though, as the engine speed increases, there is less time for that air to flow in. Now, air has weight, as we just talked about. And anything that has weight has inertia. So it has the inertia of rest, which is it takes force to get it moving. And then once things are moving, they have inertia that takes some sort of force to stop them. That force could be friction, like with brakes on a car, or anything else, any other force acting against the motion of that stuff. So with air in an engine, when you step on the accelerator, or even when an intake valve opens, the air takes some amount of time to actually get moving. And then once it does get moving, especially if it's at a high speed, flowing into that cylinder, even when the piston stops moving down and creating more and more space for air to flow into, the air will continue to flow because of that inertia. It's kind of, think about it, if you go to push a car, right? It takes a lot of effort to get the car going, so that's overcoming the inertia of rest. Once the car is rolling, it's not that hard to keep it rolling, so it'll keep on going until it encounters some sort of force that makes it stop, which, in the case of the car would be usually friction and things like that, once it hits a wall. So air does the same thing, right? So the intake valve opens, air starts rushing in, and then even when the piston stops moving downward, so the, even though the pressure is still not decreasing, because the air has inertia, it's going to keep flowing into the cylinder. So when we talk about the intake stroke, we'll get back to that in a minute. So, what is the intake stroke? So the purpose of the intake stroke is to take in either, it depends on the engine, either a charge, we'll call it a charge of air and fuel, or just air, right? So with a carburetor, with throttle body injection, with port fuel injection, the air and fuel flow into the cylinder at the same time together, right, on the intake stroke. With direct injection, the air flows in and then the fuel is injected directly into the cylinder. Either way, the job of the intake stroke is to fill the cylinder. So what happens, right, the piston moves from top dead center to bottom dead center with the intake valve open. Because that space is expanding, same amount of air, bigger space, you get a low pressure area or a vacuum. So we know that's something less than atmospheric. Atmospheric pressure pushes air into the cylinder. I'm, of course, talking about a naturally aspirated engine. If I'm talking about a turbocharged engine or a supercharged engine, then it's not just atmospheric pressure pushing air into the cylinder. It's, air under compressor pressure. So the amount of air entering the cylinder depends on a lot of things. So what's the pressure, right? So a turbo or a supercharger drastically increases the pressure. It's going to drastically increase how much air goes into the cylinder. And you got to remember, engines make power, they make more power by pumping more air. So the more air you can get into that cylinder, the more power that engine's going to make. Obviously, you have to add the correct amount of fuel for the air, but more air, more power, right? So a turbo or a supercharger is going to force air into the cylinder, forced induction, you're going to get more power. If it's naturally aspirated, then you're relying only on atmospheric pressure, and that's variable. It's variable at different altitudes, and it's variable on different days. Another thing that's going to affect how much air gets into the cylinder, and therefore how much power the engine makes, is the size of the intake valve or the number of intake valves. You can have a cylinder with one big intake valve, or you can have a cylinder with two small ones. Another thing is, how far does that intake valve open? Now, what affects how far the intake valve opens? Camshaft lobe lift, and if there are rocker arm ratio, right? So a cam can be designed to open a valve more or open it less, and this all depends on what we're trying to do with the engine. That's one thing that you're going to find throughout the entire discussion of engine performance, is that engines are designed for a purpose. Some engines are designed for low RPM, high torque operation, and some engines are designed for high RPM, so not so much high torque, but high RPM. Next thing, how long does the intake valve remain open? How many degrees of crankshaft rotation is that valve open for? And so this used to be just fixed. But we have variable valve timing, so I mean the number of degrees stays the same, but when it opens and when it closes can change. So that's based on the shape of the camshaft lobe. That's going to determine how many degrees of rotation that valve is open for. So you got lobe lift, you got lobe duration, and those are designed right into the cam. The last one, how long the intake valve remains open time-wise. So is it a millisecond, 2 milliseconds, 10 milliseconds? Some of that is determined by how many degrees it stays open, but the other thing is engine RPM. So if you have an engine that's going slow, the valve's open for a long time. If you have an engine that's going very fast, high RPM, the valve is open for a very short period of time. Even if the duration on the cam designed in there is long, the amount of time is very short because of the high engine speed. So here's when an engine will breathe the best, right? And this is, just a kind of an oversimplified statement, but when the engine is moving relatively slow and the throttle is wide open. So you have very little restriction on the incoming air, and you also have a lot of time for the air to flow in. That's when you'll get the best breathing. Now, some things with the design of the intake and exhaust manifolds do affect how the engine breathes at different RPMs. So wide open throttle idle is not necessarily where it makes its peak torque, but the amount of torque and horsepower and the way the engine breathes is definitely affected by engine RPM and throttle opening. So if I'm towing a heavy trailer up a mountain, right, that's going to keep my engine RPM down, all that load, and I'm going to have the throttle very far open. So I'm making a lot of power at that point. When I get to the top and I'm coasting down the other side of that mountain, my engine might be revving relatively high, but I got my foot off the accelerator, so my throttle's closed. Now I'm restricting the air flowing in, and the engine's moving kind of fast, so there's not as much time for air to flow in. These cylinders are not filling well at all. They're not filling anywhere near as much as they could. So the engine's making essentially no power on deceleration like that. Turns out, well, you don't need it on decel, right? Okay, next slide, we're going to start talking about the compression stroke. So on the compression stroke, the intake, the piston has reached the bottom of the intake stroke. And now I have to back up a little bit, right? When the piston reaches the bottom, I was always taught, okay, the intake stroke, the intake valve opens, the piston moves down. When the piston gets to the bottom, the intake valve closes. Not necessarily. Remember what I told you before about inertia and how once the air gets moving, it wants to keep moving? And then I also told you how the cylinder at bottom dead center, the piston is moving really, really slowly. It's barely moving at all those last few degrees at the bottom and the first few degrees on the way up. If you watch the connecting rod, it's moving more sideways than it is up or down, way down at the bottom there. So what they typically do is they leave that intake valve open well past bottom dead center. And what that does, it allows that air with the inertia to keep flowing into the cylinder even after the intake stroke has, technically ended and the piston has started up on the compression stroke. So now we've gotten to the point where the intake valve finally closes at some point after bottom dead center. The piston's already started up, but it's really not moving very fast. Now we have both valves closed. And because both valves are closed and the piston's moving up in the cylinder, two things go up. The temperature goes up and the pressure goes up. So I don't remember, I think it's Boyle's law of gas or whatever. When you put a gas like air, hydrogen, anything, when you put it under pressure, the temperature also goes up. This is, in fact, how a diesel engine operates. There are no spark plugs. The pressure gets so high that the temperature reaches the ignition point of the diesel fuel, and you have compression ignition. And so the temperature and pressure go up in a gas engine too, but they don't go up to the point of causing the air-fuel mixture to burn. That would be bad. We don't want that, right? So that would be too much temperature. So in the compression stroke, we call the amount of compression by a ratio. So if we took, 10 cc's of air in the cylinder, so that's a pretty small cylinder, and squeezed it down to 1 cc, that would be a 10-to-1 compression ratio. Let's take an example of a 2-liter engine. That's a 4-cylinder. What does that mean? That means each cylinder is half a liter, 0.5 liters. So when the piston's at the bottom, the volume of that cylinder is 0.5 liters. We could take a 1 liter bottle of, Coke or something and pour half of it in that cylinder. That would fill it. When the piston comes to the top, if we have a 10-to-1 ratio, it's going to be 0.05 liters. So squeezing it down into a much smaller space. So same amount of air and fuel squeezed into a much smaller space equals much higher pressure. And because of the higher pressure, also much higher temperature. So what determines the compression ratio? How far does that piston move? So stroke, right? So that's determined by the crankshaft design. The piston, some pistons are flat top. Some pistons have actually a dish on the top. So when the piston's at the top, there's more space. And some pistons actually are domed a little bit. So the top of the piston actually is up into that space in the cylinder head and really, really squeezing the space down to nothing. So if I have a low compression engine, it might have a dished out piston. If I have a high compression engine, it might actually have a domed piston, and anything in between might just be a flat top. I do have a video that shows the 4-stroke cycle. We'll kind of look at that. We'll discuss it a little bit. So here's a question. What moves the piston from bottom dead center to top dead center? And I'm not going to answer that for you. You think about that. So what causes that piston to move? Some force has to act upon it. That's the one problem with not being in the classroom. I can't really ask you questions. So the total volume in a cylinder is how much volume there is when the piston's at bottom, right? So piston's all the way down at the bottom. You pour liquid into the cylinder and into the combustion chamber in the head. And how much does it take? That's total volume. Now when you put the piston all the way to the top, that's called the clearance volume. So if it were a 10-to-1 compression ratio, that clearance volume would be 1/10 of the total volume. How can we maximize compression pressure? Right? There are several ways. So the more air we jam into the cylinder in the first place, then the higher our total pressure is going to be at the top of the compression stroke. If we have pistons that are domed or whatever, that's going to maximize compression pressure. If we have forced induction, turbo supercharger, maximize compression pressure. Anything we can do to make the engine breathe better will increase compression pressure. How about, bigger throttle body? How about the design of the intake manifold, the design of the intake valves, the size of the intake valves, the number of intake valves, all of these things, the lobe lift, the duration, and all that kind of stuff that we talked about before. Let me just look ahead. Okay. So now I want to talk about compression, two effects of higher compression. And let me just get my face back on here a minute. So this may be a little bit of an unusual way of teaching it here. Let me turn put this camera down just a touch. All right, that was a touch too much. By the way, the clock behind me here, over there, you may have noticed already, it always says 4:45. That clock, there's nothing wrong with the clock itself. It was designed to get its time from a government time service that used to broadcast over radio waves, and the government shut that down. So this clock, there is no way of manually setting the time. There's no knob you can turn. So it's basically dead. But I like the clock because I designed the face of it with the ECC logo, and it says Vehicle Training Center on it. I don't know how clearly you can see that. So I don't want to get rid of it. So I'm going to have to just steal the guts out of another clock and put them in there. But for now, it's always 4:45, which means it's almost time for a drink all the time. So speaking of that, and I'm not saying everybody drinks or should drink, but I want to talk about compression, and I want to compare it to something else. Compression is good. And many people think that, Irish whiskey is good, for example, right? And so you might think, well, if a little bit of compression is good, well, then a lot of compression is great, right? So compression is like Irish whiskey. A little bit may be good. A little bit more, maybe even better. But too much, and you're falling down the stairs. Okay, so too much compression, not a good thing. Just keep that in mind. What can happen if you have compression that's too high in an engine? And then another question would be, how in the world do you get compression in an engine that's too high? So let's start with the first question I asked. First question I asked was, what happens if the compression's too high? In a gasoline engine, the combustion process is started by a spark plug. And the timing of when that spark plug fires and starts the combustion process is carefully controlled nowadays by a computer. If we lose control of when the combustion process starts, all kinds of bad things happen. So if we allow the temperature from high compression to ignite the air-fuel mixture instead of allowing the spark plug to ignite it, it's going to ignite it at just random times. Also, you'll have a burning air-fuel mixture and a pressure wave beginning in the cylinder, and then the spark plug fires, and now you have two pressure waves that smack into each other. So what happens is something called detonation, and detonation is when the air-fuel mixture explodes rather than burning. It's supposed to burn steadily and provide a nice, even, steady push on the piston. If there's an explosion, you lose power and it can do all kinds of damage to the engine. I've seen spark plug electrodes knocked right off. I've seen pistons severely damaged, all kinds of things like that. So there is a video on detonation that I may not show you today, but I will show you that. Detonation's bad, and high compression, excessively high compression can cause that. So how do we run a high compression engine then? That's another question, right? Okay, a lot of engines are out there with 12-to-1 compression ratios or more. How do those things not detonate and destroy themselves? And the answer to that is octane. So when you pull up to a gas pump, regular unleaded 87 octane, 87 octane is good for your normal grocery getter cars. But as soon as you stick a turbocharger or a high compression ratio, things that are going to drive the temperature and pressure in the cylinder up, then 87 octane is too explosive. It can't handle those high pressures or high temperatures. So you go to 89, 91, 93 octane. Octane indicates a gasoline's anti-knock qualities, ability to prevent spark knock or detonation. So what octane gets you is not cleaner gas. The 87 octane has detergents in it just the same as 91 or 93. It's not more powerful just by itself. There's not more energy density in the fuel. What there is there's the ability for that fuel to handle the higher temperatures and pressures of a high compression or a forced induction engine without detonating. So that's why it's so important, that you put the right fuel. If you put high octane fuel in a car that's not designed for it, oddly enough, it could have problems with cold starting and stuff like that. And the other thing is it wastes you money. You know, if you're putting 89 octane in when you could be using 87, or when the car is designed for 87, you're just wasting money. You're not going to get any more power out of it. People will say, "Oh yeah, I get more power." Not if the car is designed for that. On the other hand, if the car is designed for higher octane and you put lower octane fuel in it, you may lose power, but not because the fuel is less powerful, but because the engines have NOx sensors. And if the NOx sensor starts going off, signaling to the computer that the engine's knocking, the computer will detune the engine enough to stop the knock. And so you will lose power that way. Not because the fuel is weaker, but because the computer has to protect the engine from the detonation that happens. So let's see if I can share the video on, let's see, close this down a bit. And back to lessons here, back to module 1. So I showed you the atmospheric pressure video. Let's do this 4-stroke cycle video, and maybe even the knocking and pre-ignition video. I usually don't do that yet, though. So, I mean, you can watch any of these whenever you want, but as far as me discussing it, maybe that'll be another time. So let's look at this video here. You have to watch an ad, I'm sure. Maybe not.
A basic lesson in the fundamentals of a 4-stroke EFI gas engine may be helpful to your understanding of Mercury products. Here are the basic components of every 4-stroke gas engine: a piston, a connecting rod, a crankshaft. As the piston travels up and down in the cylinder, this lateral motion is turned into a rotating motion at the crankshaft. The longer the stroke of the piston, the larger the displacement of gas and air occurs in the cylinder. To propel that piston, we need to ignite a tiny bit of gas and a whole lot of air. This creates expansion inside the cylinder. The fuel delivery system consists of an air intake manifold, valves, intake and exhaust, a fuel injector, and a spark plug. A 4-stroke engine is called a 4-stroke because
I wouldn't call a spark plug part of the air delivery system. I probably wouldn't call the exhaust valve that either. So I know I'm being picky, but
4 up and down motions are needed to complete the cycle. In the first stroke, the piston travels downward as the intake valve opens and a mixture of air from the atmosphere and a metered amount of gas from the electronic fuel injector enter the cylinder. This is called the intake stroke. On the second stroke, the piston travels upward, compressing the air and fuel to make a highly combustible mixture. This is called the compression stroke. At this point, the spark plug fires, sending the piston downward from the expansion of the air and gas mixture. This is the combustion stroke. The fourth stroke is the exhaust stroke. As the piston travels upward, the exhaust valve opens to release the burned air-fuel mixture. When the piston reaches the top of this stroke, the intake valve opens and the cycle begins all over again. It takes 1 up and down motion, or 2 strokes of the piston, to create 1 revolution of the crankshaft. RPMs, or revolutions per minute, is how many times the crankshaft rotates within that minute. At wide open throttle, the crankshaft may turn at 5,000 RPMs, or a dizzyingly 83 times per second. Meanwhile, the piston traveled up and down 166 times in that same second. Want to see how fast that is? Now, that's fast. Let's see it again. Amazingly, the 4-stroke EFI engine does this smoothly, quietly, and reliably for years and years of operation.
So maybe there were a couple things in there that were not 100% representative of what really goes on there. So one thing, they showed the intake valve closing as soon as the piston hit the bottom, and I've already told you that that usually doesn't happen. And they showed the exhaust valve closing on the exhaust stroke before the intake valve opened again. And frequently those are for a little while open at the same time, which is called valve overlap. We'll talk about that more when we talk about the exhaust stroke. So I'm going to go ahead and I'll go ahead and play the detonation and pre-ignition video, even though we haven't really discussed ignition timing or anything like that yet, just to show you what can happen to an engine if things aren't right. So if you have low octane fuel or lower than it calls for, or if you've got hot spots in the cylinder, glowing carbon, a spark plug that's the wrong heat range. We'll talk about, as the semester goes on, all of these things are going to be brought up. So let me turn me off here and go back to our blackboard here and look at knocking and pre-ignition. I know I already clicked on full screen, so there we go. There you see the valve overlap a little bit. So what happened is over here on the side, on the right side of the cylinder, a combustion process started where it shouldn't have, away from the spark plug. And then also the spark plug fired a little bit later, and what happens is not good. You see a little hunk of carbon fall off. Okay, I think I may have been muted when I wanted to talk somewhere in there, but that last one, in case I was muted, that last one where they showed a hole burn right through the top of the piston, I've seen that. I pulled the cylinder head off and seen a hole burn right through the top of it, and you wonder how that could possibly happen, but it does. So I think there was something else I wanted to say, but not sure I really remember it. I'm sure I'll think of it after I'm done and this is posted and you're watching it sometime over the weekend. So it's only Thursday right now when I'm doing this. So we got a lot of semester, in case I forget things, a lot of semester to talk about it. So